Hey folks, the Earthlings. Welcome to Decoding the Earth, the podcast where we dig deep into the layers of our planet to uncover the fascinating stories beneath our feet and sometimes even above our heads. I'm your host Raihan Ghani, a geologist and professor here to bring the rocks to life. Each episode will explore how geology shapes us by shaping the world around us. Ready to decode the Earth? Let's rock. Today we are talking about a clean energy source you can't see, but maybe streaming through rocks beneath your feet. Natural or geologic hydrogen. Early this year, the US Geological Survey released the first national prospectivity map of geologic hydrogen, spotlighting US regions where a hydrogen rush could begin. News outlets picked it up with headlines like drilling for clean hydrogen. And for good reason. When you burn hydrogen to generate energy, the exhaust is just water. What is natural hydrogen and why geologists care? Natural hydrogen is H2 generated and stored in the subsurface by earth processes, not produced in a factory or electrolyzer. Think of a geologic hydrogen system, a source that creates hydrogen through water rock reactions like serpentinization, radiolysis of water, high temperature cracking of hydrocarbons, or even mantle flux. A reservoir that holds it and a seal that keeps it from escaping. That's a familiar framework for anyone who has mapped petroleum plays. If you work in oil and gas, this will sound like home. Hydrogen exploration is now following the same sequence of petroleum system: generation, migration, trap and seal, exploration, drilling, production. The hydrogen window. Here is a key idea for targeting. The effective hydrogen window often sits deeper and hotter than the classic oil and gas windows. Serpentinization, oxidizing iron in ultramafic rocks in the presence of water, can generate abundant hydrogen around 200 to 315 degrees centigrade. Thermal cracking of hydrocarbons can also yield hydrogen at high temperatures. Compare that with the typical oil window of about 65 to 150 degrees centigrade. It's clear many hydrogen sources live at higher temperature and therefore deeper stratigraphic levels. That means some of the best hydrogen plays may lie beneath your conventional targets. Global case studies to US prospects. Globally, the field is moving from curiosity to structured exploration. The B project in Mali, often cited as the world's first producing natural hydrogen field, has documented high purity hydrogen and even powered village electricity for years, providing a real world template for trapping, replenishment, and materials handling. Meanwhile, in Western Australia, Constellation Resources has reported indicators of harmogenic hydrogen in over-mature shells, signaling that deep and hot exploration targets are not just ideas. In the United States, the USGS prospectivity work aggregates geologic and geophysical layers into a continental scale view, highlighting mid-continent to Great Lakes trends, parts of the Four Corners, the California coast, and segments of the mid-Atlantic eastern seaboard as areas of interest. The Public Maps Explorer is live. It is a great starting point for basin screening before you overlay your own proprietary data. Why this matters for the energy transition? Hydrogen combusts to water, no carbon dioxide from the tailpipe or turbine. And in some settings, geologic process can continuously generate hydrogen, making certain accumulation effectively renewable at human timescales. That's why you are hearing the phrase primary energy resource, not just a storage medium. Of course, rates, replenishment, and sustainability vary by site, which is why we need real basinal data and disciplined
pilot projects. How we will actually explore it? Here is a quick playbook for how a geologist might proceed. Screen prospectivity with the USGS layer, then filter by your own structural and heat flow models. Prioritize deep, hot basins, ultramafic intrusions, ophiolites, radiogenic crust, and places with helium shows, a common exploration proxy. Generation and analysis. Map where serpentinization, radiolysis, or over-mature organic cracking could operate. Bracket a hydrogen depth window with geothermal gradients. Migration and trap. Remap basement fabrics, faults, and rift geometry to identify pathways and structural stratigraphic traps. Emphasize seal integrity because hydrogen is the smallest molecule and quite reactive. Reuse legacy data. Revisit mud gas logs, soil gas surveys, and fluid inclusions in vintage core. Several recent hydrogen signals came from exactly that kind of reread. Test and pilot. Plan wells with explicit hydrogen logging, materials compatibility like embrittlement, elastomers, and safe handling at surface. Then cycle test for deliverability and replenishment. Reality check and opportunity. Prospectivity isn't certainty. Seals, microbial sinks, and leakage can kill an otherwise pretty map. And economics will hinge on co-produced gases like helium or nitrogen, market access, and how quickly we can de-risk materials and operation at scale. But the upside is compelling. A low-carbon primary energy that taps skills, datasets, and infrastructure the subsurface industry already has. My take, as a geoscientist, I'm bullish but disciplined. The hydrogen window being deeper, hotter than oil and gas means we'll lean on maturity, heat flow, and structural mapping, the same muscle memory that built the hydrocarbon industry, tuned for hydrogen chemistry. If the field stays rigorous, data-driven, transparent, safety first, natural hydrogen could become the most interesting subsurface discovery of our careers. I'm Raihan Gani. This is Decoding the Earth. If you are curious about where geology meets clean energy, keep an eye on geologic hydrogen. The story is just beginning, and it is happening in the rocks we already know.
A special thanks to Professor and Geologist Nahid Gani for directing and producing this podcast. Don't forget to subscribe and follow us on social media to stay up to date on all things geology. See you next time on Decoding the Earth.